as I remember, but because I didn't find a correct version. And you can define U, you can define, I mean, starting from the A, you can just check the dictionary of thermodynamic, I mean, of thermodynamic. In thermodynamic, in the first chapter of our book or any other books, there is a equation for the entropy in terms of Helmholtz energy. If you give me Helmholtz, I can find everything for you. Still, I can find also, for example, A is U minus Ts, for example, like that. And beta is 1 over kBt. Yeah. And U is the total energy of the system, actually. So A is the key here. A. How to find the Qn? So now the problem is that how to find the Qn. Okay, I will explain you my strategy to solve the problems. You know that you need to have the form of the energy state of the system. So if you give me the energy state, I can find for you the En, huh? For example, energy in the box, particle in the box. For particle in the box, if you give me the energy state, I can do that. So it depends to the ER. Huh? I want to tell you that normally we have a two type of the system. Two types of systems. The system with potential, okay, and the system without potential. The system with potential, we call it localized particles. Non-localized. Free particle. Non-localized means free particle. Yes, you have just two types of the example. The particle can have potential or not potential. Yeah? And still we have n number of the particles. So n is the number of the particles. Total number of particles. With the detail that you don't need it to know at the first reading of this course, I can tell you that the Qn for non-localized will be Q1 what is the Q1? Q1 beta is partition function for one, just for one particle. Because particles are the same. Huh? You have, for example, n hydrogen atom. Each one has the same Hamiltonian, same energy state. Huh? So if you consider one of them, it will be enough. But not always. If the system had potential, you needed to just write one of them multiplied to n. So this is the partition function for one system. And if you have not potential like the free particle, you can have this. Do you know what I will do is that I will solve for you now the problem of the particle, free particles, with this method. And we get the same expression as before we found. And I can solve also we will solve the question of harmonic oscillator and many other examples. Just remember that if you want to know why here n factorial appear, not appear, it's related to the Gibbs paradox. It's related to the countings. It's related to the distinguishable and non-distinguishable particles. The particles which you can label them and you cannot label them. The classical particles are almost all the same, so you cannot label them. So you needed to consider this particle for that. So 3 reasons you can find it, 3 reasons. But we don't need it now. We don't need it that. But you can yourself study more about that. What I was thinking, I was just thinking to learn you how to find the partition function. This is essential for me. find a partition function is essential. So, just have to find a simple example of the system which you can find this logarithm, this expansion. I consider a system of n photon when the total energy or the equation for the energy is nh nu. N can find this is energy for each photon. I want to find the partition function for the photonic gas. Why I give you, because this is the easiest one. The particle in the box also not so difficult, but for that questions, we have a two strategy. We needed to pass through the phase space, or we needed to use the advanced method like theta function or something. I don't want to start by the hard question, so this is the easiest one, the photonic gases. As you see from the nature of the system, so there is no potential for the system. Huh? There is no interaction, there is nothing. So is the case here. So Qn beta will be Q1 beta n factorial. So what is the Q1 beta? Q1 beta is sigma E minus beta ER En. Yeah. Okay. I can write this equation in the following form. So this quantity x is always less than 1, you can check it. Because beta is positive, h is positive, nu is positive. So it goes from 0 to 1. So I can write it as xn. Sigma xn is 1 over 1 minus x. Basic mathematics. This is Q1. So the partition function for the system will be Q1 1 minus E minus beta H nu minus n over n factorial. Just say. Okay, so I just, what I'm doing is just expand the integral. Just I expand the integral and I'm trying to use the Stirling approximation. Can I write that n ln n minus n over beta? So this is the a. Just making the derivative of this, you can find the entropy. S is minus partial derivative of A with respect to beta. And S is minus partial R with respect to beta. Minus partial beta here is expression. And beta here, N 1 minus E minus beta H nu. And n minus n over beta. So S over N will be just make the derivative of that, huh? You can take the derivative of this expression. So 1 minus 1 over beta squared, logarithm 1 minus beta h nu minus 1 beta e. I want to take the derivative of that. So h nu e minus beta h nu e, 1 minus e minus beta h nu e, plus 1 over beta h squared. Just like playing with this. So this expression is this is the entropy of photonic gas in any temperature. I want to ask you, maybe I think I don't have any error here for the calculations, but anyway, yeah, here just logarithm n. We have ln n minus 1 here. So ln n. But you know that the n bigger, so ln n minus 1, I can write ln n just. You can find also the u, so u is r plus ts. Huh? You can find. So a is minus on the r on the beta. What is the t? T is beta is 1 over kbt. So t is 1 over kb beta. Kb beta. Everything is written in terms of the A. You can do whatever you like. Just find the entropy, you can continue and find all the functions. What I want to ask you is that this entropy, there is a two limit for that. The high temperature limit when the beta tends to 0 and the low temperature limit when beta tends to infinity. For these two limits, I want to find the entropy just to see what will be the form of entropy here. So photonic gas is the easy example actually. But that's I can't do by hand because we needed to. I can, but I'm afraid maybe we do the mistake. So you needed to take the Taylor series, not Taylor series, the series expression, Lorentz series from this. So this function should be expanded for the beta tends to the 0 and beta tends to infinity. The one is easy for me to find is that when the beta tends to infinity. So the low temperature system, low temperature regime, I can do by hand now. You will see how. Low temperature means that T tends to 0. So you expected that here the quantum effect will be very important, no? Quantum effect. Because lower temperature is the regime for the quantum regime. So just remember that beta minus h nu will tend to the 0 in this case. So I needed to take the limit of this expression when, oh, that's also difficult to do. But anyway.
You get 0 over 1 over beta squared the first term.
Yeah, I know what you say, but this is also tends to 0. 0, 0. What's the 0? 0 over 0. And that's, I know, this I can cancel this. But this will be 0 or 0. So it will limiter, so limiter S, when beta tends to 0, will be limiter, beta tends to infinity, and logarithm. This limit is, it takes work to do that, so you can do it by the mathematical or make that you can find it. Anyway, you will get something non-zero, definitely. You will get something
Can we take the limit and then substitute? Since we got 0 over 0?
No, I don't talk about how to do the limit. So you needed to make the asymptotic series of this function, asymptotic series. Needed to, this is not a real limit, asymptotic limit. I mean this will be something, for example, will be something like S0 constant plus a parameter when beta tends to infinity. If you want to find, you can find it. That's you can find just making the table set of this asymptotic limit, asymptotic series, this function. What you noted is that you, for any function like that, this is a general Taylor series. You call it Laurent series. Laurent series. Any function can be expanded like that, and the coefficient given as the n factorial over 2pi integral de frontale f t minus I. This is a contour integral Tn dt. Complex variable. You need to go and see the from Arfken, Weber, chapter 719 or something. You can find the information about the Laurent series. So you can do the Laurent series here and you can find. For beta tends to the 0, also for tends to the 0, I think the situation is more not very comfortable also. When beta tends to 0, look at what happens. So this will be 1, 1 minus 1 is 0. Again 0. And here 0. So 0 is 0. You need to again to use the Taylor series. So high temperature limit, I write here, but you don't need it to write before that. When beta tends to 0, it's just the Taylor series of S around beta 0. I guess that it will be something, we don't know that, it will be something S0 plus R beta M plus something. You can find it. Maybe it's a logarithm, maybe here logarithms. Logarithm beta maybe N, something like that. You needed to go and find it, the Taylor series. It's done in the book. It's done, so you can find. The other example which you think is easy but not easy is the particle in the box. So I want just to write for you that what is the difficulty to find the partition function for the free particle in the box in canonical forms. What is the difficulty? I want back to this equation, so everything is related to that, sigma minus beta En. And definitely you know that the energy state came from the Schrodinger equation, huh? Energy state should be found from the Schrodinger equations. What is the En? Look at that. This is the Schrodinger equation. Psi n, huh? H psi n is En psi n. So what is the En